Hey guys, today we're going to be utilizing percent composition of compounds to find the empirical formula. If you need a quick review on percent composition, feel free to head back to that video real quick, review it, and then come back to this one before you get going. Now, empirical formula of a molecular compound is going to be the actual ratio of each atom of the element in that compound. What this means is if you're going to look at the molecular formula, which is going to be the exact number of atoms in a compound, the empirical formula is going to be the most reduced ratio of that. For example, C4H6O2 has an empirical formula of C2H3O because the ratio of 4 to 6 to 2 can be reduced down into an empirical ratio of 2 to 3 to 1. So the way we actually just did that was we simply found the greatest common factor of all of the atoms in the compound, and we simply divided by that. So for instance, our situation here, we had a greatest common factor of 2, therefore every single value of the subscript is going to be divided by 2 to give us our empirical formula. Empirical formulas are only utilized in molecular compounds. Now the reason for this is because if you remember how we wrote the formula for ionic compounds, we're already in our most reduced form. For instance, with magnesium oxide, MgO, even if you do the crisscross method and you get Mg2O2, remember how we reduced that down to just MgO to give us our empirical formula. And this is because ionic compounds, when they're in their solid form, are in a different type of structure than the covalent compounds that we're dealing with here. So the focus of today's video is going to be to use percent composition to find empirical formula. Percent composition, remember, is the percentage by mass of each element in a compound. In other words, if a compound is 20% oxygen, that means 20% of the mass of that compound is made up by oxygen atoms. Let's go ahead and start by looking at an example problem. Now in this example problem, we're given the fact that we have 72% of a compound by mass, which is chlorine. We have 24%, which is carbon, and we have 4%, which is hydrogen. Now, the easiest way to solve a problem like this is let's just assume we have 100 grams of our sample. This makes things easy, because now we can convert from percentage into grams. So because we had 72%, which is chlorine, that means that in a 100 gram sample, 72 grams would be chlorine. Same thing with carbon, where you'd have 24 grams of carbon, and hydrogen, you'd have 4 grams of hydrogen. Now this makes things simple because of the fact that we know how to go from the number of grams of a substance into the number of moles of a substance. And with the empirical formula, this ratio that we're looking to gain is simply the mole ratio, the ratio of moles of each element in the compound. The way we solve this, we take our 72 grams of chlorine and we're going to divide by the molar mass of chlorine. We take our 24 grams of carbon and we divide by the molar mass of carbon. We take our 4 grams of hydrogen and we divide by the molar mass of hydrogen. This results in 2 moles of chlorine, 2 moles of carbon, and 4 moles of hydrogen. Now as you can see here, these are not fully reduced because we can actually divide by the smallest value. So what we're going to do is we're going to divide by the smallest value, which is 2, which results in an empirical ratio of 1 mole of chlorine, 1 mole of carbon, and 2 moles of hydrogen. This means that the empirical formula for our compound here is CClH2. Again, this is the empirical formula. So we don't know the molecular formula yet, but we do know the empirical formula based on the percent composition by going through this method. So now let's look at a second example. Here we're going to look at a compound which is 37.51% carbon, 4.2% hydrogen, and 58.29% oxygen by mass. Now, we need to find the empirical formula of this compound, so just the same as we've done before, we're going to take each and assume that we have 100 grams of the substance. This means we have 37.51 grams of carbon, 4.2 grams of hydrogen, and 58.29 grams of oxygen. We now divide each by the molar mass, which means we divide the carbon by 12, hydrogen by 1, and oxygen by 16. This means that we have ratio of 3.13 moles of carbon, 4.2 moles of hydrogen, and 3.64 moles of oxygen. We divide by the smallest one, which is going to be that of carbon. Now when we do this, you'll notice that not every result is an even number. Empirical formulas, remember, must be whole numbers, which means we're going to have to multiply. Now, this one's tricky because you can see that we have numbers that don't really look clean. Carbon's 1, obviously, because we divided it by itself, but the hydrogen is 1.33, and the oxygen's 1.16. These are kind of weird numbers. Now, the 1.33 is not close enough to either 1 or 1.5 to be able to round it. However, the 1.16 is. This is going to have some wiggle room. In general, I'd like to say that when you're going to round to a whole number, it's got to be pretty close. There's some wiggle room here, though, all right? Because obviously there is a way to get that 1.16 to a whole number, but we're going to go ahead and round that down to 1. There's no hard and fast rule, but generally if it's not exceptionally close to either a whole number or a half or a third, I'm going to round it in that situation. So this 1.16 I'm going to round down to 1, but the 1.33 we're not. This means we have to make that 1.33 a whole number. We do this by multiplying it by a factor that gets it to a whole number. In this case, because 1.33 is 4/3, multiplying it by 3 would get it to a whole number of 4. If we multiply every single value by 3, this means we're multiplying the 1 of carbon by 3, the 4/3 of hydrogen by 3, and the 1 of oxygen by 3. This means we have an empirical formula of this compound of C3H4O3. Again, there is some nuance to this, and it can be tricky sometimes, but in general, you're going to see more obvious numbers in your problems. It's just if you do see a problem like this where you don't have a number that's really obvious, you are okay to round it. All right, just be careful while you're doing so. Here's an example problem that I want you guys to try on your own. Pause the video, take a few seconds, all right, or minutes if you need to. Work through this problem. If you get stuck or get an answer, I want you to unpause the video and then we're going to work through it together. All right, now you've had a few seconds to work through the problem. Let's go ahead and work through it together. We're going to assume that we have 100 grams of our unknown compound. This means that we have 28.2 grams of nitrogen, we have 20.8 grams of phosphorus, 8.1 grams of hydrogen, and 42.9 grams of oxygen. We divide each element by its molar mass, which leaves us with 2 moles of nitrogen, 0.68 moles of phosphorus, 8.1 moles of hydrogen, and 2.68 moles of oxygen. We divide by the smallest value across the board. That's going to be that of phosphorus, the 0.68. So we end up with a ratio of 8 nitrogen, 1 phosphorus, 11.75 for hydrogen, and 4 for oxygen. We need to make sure that we have whole numbers, which means we have to multiply every one of them by 4. This means that we have an empirical formula for this compound of N12, P4, H47, O16. So our empirical formula here is extremely large, but still in the most reduced form. So in other words, your empirical formula does not have to be simple. It can be extremely complex depending on the complexity of the compound you're looking at. In the last practice problem, I'm going to challenge you guys here. I want you guys to now think about what we've learned and extend it, because now I'm going to give you the empirical formula, and I want you to tell me what is going to be the percent composition of this compound. So our empirical formula that I'm giving you is C2H5O. And I want you to take a few minutes, pause the video, and solve for the percent composition of this compound. When you're done or get stuck, unpause the video, come back, and we'll work through it together. All right, now you've had a few minutes to try to solve this problem. Let's go through it together. This one was tricky because in the past we went from percent composition to empirical formula. We did this, remember, by starting by assuming we had 100 grams of the substance. In this case, we're actually starting with the number of moles of the substance effectively, with the subscripts of each element in the compound. So instead of going from grams to moles, we're instead now going from moles to grams. The way we do this is by multiplying by each element's molar mass. So carbon, which in the compound has an empirical ratio of 2 moles, we're simply going to take that subscript 2 and multiply by 12. This is going to give us a number of grams of 24. Hydrogen, we're going to multiply the subscript 5 by its molar value or molar mass value of 1 gram per mole, giving us 5 grams of hydrogen. And oxygen, it's going to take the 1, the ratio of 1, and multiply it by 16, which gives us the number of grams of 16. Once we do that, let's assume we have 1 mole of this compound. If we have 1 mole of this compound, that means we have a total of 45 grams of substances. We would have the 24 grams of carbon, 5 grams of hydrogen, and 16 grams of oxygen. So now let's assume we have 45 grams of this substance. What percentage was carbon? Well, all we have to do is take 24 and divide it by our 45. What percentage is hydrogen? Well, we take our 5 grams and divide it by 45. And what percentage is oxygen? We take our 16 grams and divide it by 45. This means that we would have percentages, if we multiply each of those proportions by 100, of 53.3% carbon, 11.1% hydrogen, and 35.5% oxygen. So now you guys can work both forward from percent composition to find empirical formula, but you can also work backwards from empirical formula to find the percent composition. All right, so that wraps up today's video. Let's do a quick recap. We started by reminding you what percent composition is, and then discussing how you can take percent composition and find the empirical formula of a molecular compound with that value or with that data. Once we did that, we did some practice problems, and then finally we challenged ourselves with a problem of going from the empirical formula back to percent composition. I'd like to thank Sue Rajanala for writing, filming, and editing this video. I'd like to thank you guys so much for watching, and I'll see you in the next one.